Okay, let me share the screen. Acha, so we were discussing about polyphase circuit, mostly the three-phase system. These are the advantages which I wrote in hand that I have written here. And then these things we have uh, explained. We were discussing about the balanced three-phase system, right? So what happens when the balanced loads are used, and what happens when we take star connection and then delta connection? These are the balanced case. And when we have the balanced YY connection, this is your source and this is your load. And if you are using balanced load, then your neutral current will be equal to zero, so there won't be any drop here. So these are some example. Here you are given if we just go like this, let us solve it. We have the source from the alternator, we are getting this, or from the three phase Y connected or star connected transformer, we have connected these three loads. So if we want to redraw it, we can draw like this. So you can draw it like this. This is 100. This is 100 angle minus 120, and this is 110 minus 240. And along with this, you have connected three. This you check, it is 5 minus j2, so it is basically capacitive load which is connected in series with the inductive load, because we know that inductive reactance is equal to j omega l, and capacitive reactance is 1 by j omega c, and that turns out to be minus j by omega c. So this is a capacitive load and this is inductive. And that is same for all these three cases. So these things happen because there is one thing which is called Ferranti effect. There we use the we use capacitance to improve the power factor. So for power factor improvement, we do this kind of thing. Anyway, so this is a capacitive part, and that is in series with the inductive load. So we can add them up and we can write it as 15 plus J6, right? So that is same for both the cases. So this is again star connected here like this. So this is 15 and this is J6. So now what you are asked, calculate the line currents in the three-wire YY system. So if you can do it only for this phase, so as we know that it's a balanced system, means if we have a neutral wire, if we can connect it between these two, then this IN to be equal to 0, right? So what you can do, you have the phase voltage provided. So phase voltage is given, and you know that what is your in phase impedance. So this is your Z, which is equal to 15 plus J6, right? So this is your impedance per phase. So if you can calculate in one phase your line current, then for the other case it will be just 120 degree and 240 degree apart. So you can calculate your IL here, which is equal to V divided by V phase by Z phase, because IL is nothing but your I phase, isn't it? IL is your I phase. So I phase is basically it is V phase is 110 angle 0 divided by 15 plus J6. So what you have to do? you should again change this 15 and 6 to in the polar form. So 110 angle 0, then 15 comma 6. I'll just a minute, I'll get the calculator and let you know what is the value. uh, Hold on for a second. So if we compute the impedance for it, we should use the command polar and then um, 15 comma 6, and that turns out to be 16.15 angle 21.8. So your line current here, this is same as phase current, and that turns out to be 110 divided by 16.15, which is 6.811 angle minus 21.8. So if this is your line current for phase A, then for phase B it's simply 16.811 angle 120 plus 21, so it will be 141.8, and for the other one it is 16.88. Only the phase will change, so 240 then 21, so minus 261.8. Okay, so this is how you can solve this. Now this is the balanced Y delta connection. This also we have seen, and then we can also change from the delta to star. The way we used to convert for the resistance star delta conversion, same thing holds here for the AC circuit. So if you want to find out the impedance for this, then what will be the solution for it? It will be, you will see that if this is a balanced thing, then your Z phase will be equal to Z delta divided by 3. Okay, so what was the formula? I forgot. It is R1 plus, can anyone repeat what is, how can you change from delta to star? Is it, it
So
is
it's R1 plus R2 plus R1 R2 by 3.
R1 plus R2 plus R1 R2 by 3. I think it is from star to delta. Okay, anyway, so if if it is Z1, Z2, Z3, then it is actually, if all are same, then it is Z plus Z plus Z, that is equal to your, if this is phase, that is equal to Z delta. So you can find out what is this. So this is how you can convert, and then you can solve it. And whenever you are solving like from start to start, then you should remember that your I L is equal to your I phase, and again this problem has come. I don't know why it is happening. Anyway, IL equal to I phase, and V phase is equal to VL by root 3. So these things you should remember when it is star, and when it is delta connected load, VL is equal to V phase, and IL equal to I phase by root 3. So this relation, if you can remember, then your calculations will be all right. So there is one more example where you have a balanced ABC sequence Y connected source. Source is Y connected as it is shown. It is not shown, and we have a delta connected balanced load of this. It is diagram wise it is wrong. It should be source, which is Y connected, and you have a delta connected balanced load of 8 plus J4. That means a capacitive load. Sorry, inductive load per phase. Calculate the phase and the line current. So whenever you have given, just from here it is given that Y connected source with VAN is equal to 100 angle 10. So what happens to your what happens to your line VAB. I mean, when you have to find out your line current, line voltage will be VAB, right? So if it is, let me draw it like this. This is your VA. This is your VB. This is your VC. So VA is given here, and that is connected with a balanced load of delta connection. So you can either find your delta, either you can keep it like this, you can find out your line to line voltage here, and or otherwise what you can do, you can change this delta, which is a delta connected load, into star, and in that way also you can solve. So then your delta connected impedance will be changed to star connection by 8 plus j4 3. So this is going to be your Z per phase. So you know what is your Z per phase, you know what is your voltage per phase, then you can calculate your line current, which is same as your phase current. Okay. So this is how you can calculate it. Or there is alternative approaches. You can find out this. What is your VAB? This you can find out. VAB is equal to VA minus VB. So it is basically your VA is 100 angle 10 minus 100 angle, it will be uh, minus 110. So either you can change the from polar to rectangular, or you can just do the phasor sum of it. So it will be root 3 into 100. And then what will be your angle? If it is VA, if VA is in phase, then it will be leading. So you can just take 30-degree addition. So it will be, your value will be 100 root 3 angle 10 plus 30, so 40 degrees. This is your, for A phase, this is your line voltage. I mean, between A B, this is your line voltage, which is VL, line to line voltage or line voltage. And for this, but within these two, you have a delta connected load, which is 8 plus J4. So that you divide, you change these from here, I mean Cartesian to polar, and that will supposed to be, this is 100 root 3, and this will be it will be how much it is, 4 into 2, so 4 root 5, isn't it? It is 4 into 2, that whole square. So 4 square plus 2 square equal to 4. So 4 square into 4 plus 1, so 4 root 5. And angle, let us just check it, 8 comma 4, it is 8.944. This is equal to that angle 26.5. So what you get, 100 into root 3 divided by 8 8.944, that is to be it's a mistake. So 1.732, that means 173.2 divided by 8.944, that comes out to be what? It is 19.364. Angle will be 40 minus 26, so it will be 14. Okay, so you get this as your line current. Okay. And then if you have to find out the phase current, then you know for the delta connected system what is your line current, then from there you can find your phase current, no harm in it. Okay, so this is how you can solve, and you can cross check with the other method anyway. So when it is a balanced delta delta, that is also, you know what is your IA is equal to uh, root 3 into IAB. Okay, because this is the phase current and this is a balanced load, and your this angle VAB is VL is equal to V phase. So you proceed for the calculation. Then given an example, okay, solution is not provided. After that, it's not given. Okay, balance delta connected load having an impedance of 20 minus J15. So it is a capacitive load. Okay, is connected to a delta connected positive sequence generator having 330 angle 0. Forget about the positive sequence generator now. There is I am not going into the details of sequencing. So let us just take simply a delta connected generator. So you have a delta connected generator like this. So you connect this like what you have to find out VAB, that means your line to line voltage is given, which is 330 angle 0. And what else is given? A balance delta connected load having a impedance. So impedance is given. So you know VL, which is 330 angle 0. You know ZL, which is 20 minus J15. So that you can convert. If you do not have any question, please mute yourself. So this is actually 25. Angle will be what? Plus or minus? This will be minus, na? This will be capacitive. So minus 36.87. Okay. So you can calculate what is your ZL. You know what is your VL. Then you can find out what is your IL. So your IL will be VL by ZL. So it is 330 minus 25. Sorry, I put an unnecessary degree sign. Plus 36.87 because this is 0. So what will be the value? It is 330 by 25. So that turns out to be 13.2 angle 36.87. So what will be your phase? I phase per calculate the phase current. So I phase will be root 3 by IL by root 3. So 13.2 by root 3, and it will be 30-degree lagging. So 36.87 minus 30. So 13.2 divided by root 3 turns out to be 7.621 angle 6.87 degree. Okay. So if you can calculate this, then you can find out what is the net power drawn by the load. So what will be the active power consumption? It is root 3 into VL into IL into cos phi. What is your cos phi? This angle. So you can put root 3 into VL is 330. IL you found out to be 13.2 and cos phi is this. So it is cos of 36.87, which is zero point 0.8. So your final answer you can get 330 into 13.2 into zero point 0.8 into root 3, right? So it is 6.035 kilowatt. Okay, that is the load requirement of the power from the load. Okay. now let us take a few more example and then we'll go for the power measurement using wattmeter. How we can measure the three-phase power using wattmeter. So we given a problem, we have a three-phase. Okay, go back to that problem. Hmm. A three-phase motor, induction motor actually. It is induction motor. Takes 10 kVA. 10 kVA means instantaneous power is given. Volt ampere is given at zero point 0.6 power factor PF lagging. Okay, from a source of 200 220 volt. Okay, it is in parallel with a balanced delta connected load. Delta connected load with impedance 6 and capacitive reactance of 12, so it is minus 12 ohm. This is impedance. Okay, so what you have to find out, find the total volt ampere, power, line current and power factor of the combination. So we need to find out total VA. Number 2, we need to find out the power consumption after this parallel connection, active power, that means then your IL, and then number 4 is what is your effective PF now. So what was there, initially you have connected with the 220 volt. Okay, and with that you are connecting, it's given a three-phase motor, that kVA is given, power factor is given, that means you know what is, it is a lagging inductive load, volt kVA given and volt source is given, so you can find out your effective what I mean what is your effective line current for that particular motor. Okay, and then you can convert your delta into star, and then from there you can take the combination of these two, or you can convert the delta of the motor. Usually we assume that the motor is star connected. Okay, so we it is nothing is mentioned, means first you have to assume and solve. So let us say it is given supply is star, motor is star connected. Okay, so then what to do, then you find out your first of all, given V into A, which is equal to 10 into 100, that much volt ampere is given. This is your volt ampere. So if you know the volt ampere, then if you know your line voltage, which is 220 root 3 VL IL equal to 10 into 10 power 3, 10 to the power 3. Why? Because we know that root 3 VL IL cos phi is equal to total power. So we are given root 3 VL is known to us, IL we need to calculate, cos phi is known to us, which is zero point 0.6, and here kVA is given, so 10 into 10 cube into zero point 0.6. So I have not written zero point 0.6, so directly I have calculated this. This is your IL, which is turns out to be 16.25 ampere. Okay. So then what is the impedance? You know the voltage, which is VL equal to 220 volt. You know IL equal to 16.25 ampere. So what is your ZL? Equivalent load is equal to 220 divided by this 26.25, which will comes out to be okay. So if we need to find out per phase, because it is told that supply is star and motor is star connected, we have taken line voltage to be 220. So to find out your phase voltage, if we want to find out Z phase, then we can find out V phase divided by I phase. So we can write this, you just remove V phase, we can write VL by root 3, and I phase is equal to IL when it is star connected. So we can write 220 divided by root 3 into what is your IL? This is 26.25. Please bear with it. And it comes out to be 4.84 ohm. So you get it per phase, and then next, once you get per phase impedance, then you know the power factor, then you can express it like, if you know the power factor, then from here you can write it as cos inverse. So Z phase can be written as 4.84 angle cos inverse zero point 0.6, because it is lagging, so it will be plus. So we can find out what is your angle. So it is cos inverse 0.6, and that is equal to 53.13. So 4.84 angle 53.13. So again, if you change from rectangular to polar, it will come as 4.84 into zero point 0.6, because that is cosine, and another is zero point 0.8. So it is 3, and it will come as not 3, actually it is 2.904 plus j zero point 0.8 into 4.84, which is to be 3.872. So now you have a star connected source. This is 220. Line to line is given, so line to phase is phase is this. I mean, line to neutral we should call it. These are known to us. Now with this we have one star connected load. We should not write it as only resistive. So this we have connected, right? And that impedance per phase is 3 point 2.904 plus j 3.872, that we know. On top of that, there is a another load which is connected in parallel in delta. So there is one more delta connected load which is in parallel with these two. So either we can convert this into delta and then we can solve, and then this also we should take as delta. That we can get easily, because delta means it is 220 volt, that only we need. So that is one approach. Another approach is this delta, which is given. স্যার ক্লাসে আছি আমি, হ্যাঁ আমি ক্লাসটা, হ্যাঁ স্যার ক্লাসে আছি আমি, পৌনে একটার সময় শেষ হয়ে যাবে। হ্যাঁ হ্যাঁ ডিপার্টমেন্টে, হ্যাঁ 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 স্যার আসবো আমি, হ্যাঁ ঠিক আছে। Okay, so this is your per phase, you got it, and here it is given, which is 16 ohm plus minus j 12. Okay, and this is delta connected. So what you have to do, you have to convert this to star so that you can take the parallel of this, because then in par phase it will be same. So what you have to do, you have to change this delta into star and then you will get it to be, so your uh, connection will be changed to like this. Forget this. So this, and this is in parallel with another one. This is 2.9 plus j into 3.8, and here this is 16 by 3 j into 4, right? So these two are in parallel, so accordingly you have to connect the other thing. So now these two stars are in parallel connection. So now this you connect it with load. So then what to do here, balanced means this is your neutral point and that is equipotential. So no need to get confused. So nothing, balanced load means it is connected but there is no current flowing through it. Okay, so that's why we have not joined anyway. But if that is there, then what you have to do, you have to get the parallel connection between 2.904 plus j 3.872. This has to be in parallel with 16 by 3, which is 5.33 minus j into 4. So if you solve this by usual z1 z2 by z1 plus z2, that will come out to be, if we do this solution, it will come, I am writing one step because it is solved a priori. So 3.91 angle 17.17. So this you get. So now this is your effective par phase, effective impedance. Okay, so then if you know this is your par phase impedance, then you can find out the other thing, which is now what is to find total volt ampere. So total volt ampere is root 3 VL IL. Now if you can find out I phase, then that will be same as IL. So IL is equal to I phase is equal to 220 by root 3, which is V phase, divided by 3.91 angle 17.17. So that turns out to be 32.5 ampere angle minus 17.17. Okay, so that you get. So if you know IL, then you can find out total volt ampere, which is equal to root 3 into VL into IL. So root 3 into 220 into 32.5. So if you calculate that, that will come out to be 12.37 kVA.
Hmm.
Okay, so once you get this, this is your total volt ampere, then power factor will be cosine of 17.17. Please mute yourself if you do not have any question. So it will turns out to be 955. So this is your power factor. And what is your total power consumption? Total power consumption is equal to 12.37 into 0.955. That is equal to your kilowatt. Okay, so that comes out to be 11.81 kilowatt. So you can calculate volt ampere, you can calculate what is the power consumption, power factor, all those things. Okay, so this kind of problem you should solve. And just if you remember this relationship between the line and phase voltage for star connection, line and phase current for the delta connection, and then if you do the star delta conversion, when you have the combination of these three load, then it will be easier for you to solve this problem following this approach. Okay, so whatever we are discussing, it is all about the balanced three phase circuit. There is no unbalanced load anywhere. So if that is done, then let us now quickly go through the part which is about the power measurement using wattmeter. So you have a, this is your supply, and this is your load, say. Uh, Forget these two lines, this is joined somewhere here. Okay, so when we'll use wattmeter, then what to do? We have to connect our current coil and pressure coil. If we use 3 wattmeter, then we'll connect our current coil somewhere here of the wattmeter and pressure coil somewhere here. This is your pressure coil. So it is connected between this. This is your 1 wattmeter. If we, it's like this is the current coil. This is your load, and this is your pressure coil, and that is connected like this. Again this is happening. This is your load, this is the wattmeter, this is CC, this is PC, pressure coil, and you connect like this. And for each phase you have to connect like this when you use 3 wattmeter. And similarly, when you connect your delta connection, then accordingly you should join it. So whenever you use 3 phase wattmeter, it is straightforward. You have to connect the correct current coil in CC and in series, and pressure coil across the delta, across the load. Okay, so this is one thing. And then it is using 3 wattmeter method. So here there will be 1 wattmeter, here there will be another wattmeter like this. It's looking very bad actually. uh, I don't know why it is coming so many times. So if I'll try to redraw, I don't know whether I will be able to do it or not. Same thing is happening. So these are the CC, CC, CC. Here is a PC which you connect like this. So this is 1 wattmeter. This is your PC which is connected like this. This is another wattmeter. Wattmeter 1, wattmeter 2. This is PC. PC should be connected like this, not here across the load. So this is another wattmeter, wattmeter 3. So then what is happening? You are measuring. If you take the sum of this W1, W2 and W3, you will get 3 into V phase into I phase into cos phi, because you are using same load. Okay, same balanced load, so you will get like this. But we can always reduce the number of wattmeter, like we can use 2 wattmeter, and based on that, using your 2 wattmeter, we can measure the 3 phase power. So for that, how we can make our connection, let me do it for you. We are using balanced load, then only we can do this. Otherwise we should use 3 wattmeter method. Only for the balanced load you can do this. And say you have the balanced star connection, I mean supply. So you are using, this is your CC for W2 and this is your CC for W1. Your pressure coil is like this, which you connect between two line. So between, if this is A, if this is B, if this is C. So between A and C you connect this, your PC. This is your wattmeter 1, and here between B and C you connect your PC. This is your wattmeter 2. Then what will be the measurement of the wattmeter reading, what actually they are measuring? Let's see. So we'll see that if we take the sum of these two wattmeter, we'll be able to find out your three phase load, where this is Z angle theta, right? So now let us just draw the phasor diagram, then only it will be clear to you. I am proceeding to the next slide. So, or I'll try to draw it here. Enough space is there. So we first draw the, this is in the star connected. So this is your phase current VA, VBN. So I'll write like this, AN, VCN. Now what will be your current? Current will be theta degree lagging. So this is your I, this is theta. So what we are measuring with this current coil, we are measuring IA. This is your IA, IB, IC, all are same. So we are measuring current IA, and we are measuring the voltage drop between A and C. So VAC is actually VA minus VC. So if we take this side, this is minus VCN. Then if you take the phasor sum of these two, you will get VAC. So what will be this angle? This is theta. This is 30, right? And this is also 30. So what is the angle between VAC and this IA? This is actually VAC into IA into cos of 30 degree minus theta, isn't it? This is what your wattmeter will measure. VAC is measured by the pressure coil and current coil is measuring IA, and within them the angle is 30 minus theta. This is wattmeter reading 1. And for the other one, wattmeter 2, it is measuring current B, IB, and the angle measurement between B and C. So if we have taken already VC, so it should be somewhere here. This is your resultant of VBC, and this angle is again 30 degree. So we can write W2, which is equal to VBC into IB into cos of 30 degree plus theta. So whenever VAC and BC, IA, IB for the balance source, it will be same only. So it is, we can write it as VI, and we take the other thing. So if we add them up, W1 plus W2, then we can get it as V into I into cos of 30 minus theta plus cos of 30 plus theta. So you will get Vi cos 30 cos theta into 2. So cos 30 is root 3 by 2, isn't it? And cos 60 equal to half. So it is V into I into root 3 into cos theta. So you get what you are supposed to get as per the power measurement, which is with root 3 into VL IL cos theta. So if your thing is delta connected, then you will get VL equal to V phase, and I phase you can write as IL by root 3. So 3 into VL into IL by root 3 cos theta. That is your total power consumption for delta, which is root 3 VI cos theta. And for the star connection, it is 3 into V phase into I phase into cos theta. V phase equal to root 3 VL by root 3. So you'll be getting IL VL root 3 into cos theta. So using 2 wattmeter method, you can get the total power consumption for a three-phase circuit, which is very interesting to note. And if we subtract it, if we take W1 minus W2, we will get it as uh, instead of this, we'll get uh, V into I into 2 sine 30 sine theta. So we'll get Vi sine theta. Okay, so this is your uh, now if you multiply this with root 3 into W1 minus W2 will give you your reactive power. So using 2 wattmeter method, you can find out your active power. W1 plus W2 is your active power. W1 minus W2 is your reactive power. Sorry, root 3 into that. So we can write down that theta power angle is equal to tan inverse root 3 into W1 minus W2 divided by W1 plus W2. Okay, so this is your power factor, or if you can calculate cos of that, you will get your power factor. Okay, or if you have your V and I known, and you know W1 plus W2, so from that you can find your power factor. So when your W1 will be equal to W2, when W1 is equal to W2, then this will be equal to 0. So theta will be equal to 0. That means you are using resistive load. Okay. So I don't know next class how much we will be able to discuss it. Maybe I have to take one extra class in the next week, or sometime just before your exam, because we'll be having only one more week left before your exam, because 1 week before, just before your exam, there will be laboratory viva and all, and I'm doubtful how much classes will get there. Okay, so we have to arrange one extra class sometime in this week, in the upcoming week. Okay, any query?